Welcome to the deep dive. We're jumping straight into the world of large language models. The tech behind those chatbots and AI assistants we're all starting to use. They're amazing at generating text.
They really are remarkable. But there's this fundamental challenge. They can be slow. Really slow sometimes. They usually generate text just one token at a time.
Like building a sentence word by word, almost.
Exactly. And this process, it's called autoregressive decoding. The weird thing is the bottleneck isn't usually the heavy math. It's moving data. You have to pull these massive models, billions of parameters, from memory for every single token.
Ah, okay. So it's the fetching, not the thinking. That takes time. And that's why researchers are always looking for, clever ways to speed things up without hurting the quality, right?
Absolutely. That's precisely what we're digging into today. We looked through the sources you sent over, some really interesting papers focusing on a technique called speculative decoding.
Speculative decoding, okay.
And specifically a really novel, very efficient approach they present. It's got this great title, Token Recycling, Turning Trash into Treasure.
Turning trash into treasure. I like that. It definitely makes you wonder what trash they're talking about. So our mission here is to unpack these sources, really understand what token recycling is technically, how it works, why it's such an innovation compared to what's out there, and, what its performance means for you using faster LLMs. And yeah, this is all based on the material you provided, so let's get into it.
Okay, so just to recap the main problem. Standard LLMs generate token by token, each one depending on the last. It's sequential, slow, lots of data movement.
Right. And speculative decoding is the key strategy to fight that bottleneck without changing the output. Yeah. It's lossless, they say. What's the core idea there?
Yeah, the core idea is pretty smart. Instead of just waiting for the big, slow LLM to generate the next token, you use something faster, maybe simpler, to guess a few tokens ahead. Like a whole phrase.
A draft, okay.
Exactly, a draft sequence. Then you take this draft to the main LLM and ask it, basically, is this right? And you check the whole draft sequence in parallel.
Ah, using the hardware's parallel processing power.
Precisely. If the guesses were good, you can accept, say, 3 or 4 tokens in the time it normally takes to generate just one. You skip steps.
Makes sense. And the sources mentioned something called tree attention, taking it further.
Yeah, tree attention is a refinement. Instead of just checking one linear draft sequence, it lets the main LLM check multiple potential sequences at the same time. Imagine the guesses branching out like a tree.
Okay, so you can explore a few different paths simultaneously in one go.
Right, all within one forward pass of the main LLM, which is efficient.
Got it. So looking at the landscape in these sources, where does token recycling fit in? How does it compare to other speculative methods?
Well, the sources kind of split them up. First, you've got methods that need extra training, like you might train a smaller draft model specifically to make these guesses.
Okay.
Or you might add special modules like Medusa or Eagle use. They work, but it's a lot of overhead. You have to train these extra bits for every LLM you want to speed up, manage them. It's resource intensive.
Right. Sounds complex and maybe costly. What's the other category? The training-free ones?
Yeah, the training-free, retrieval-based methods, they try to find good guesses without needing new training. Think REST, PLD, look ahead.
And the sources found issues with those.
They did, yeah. REST, for example, builds this huge database of sequences from, like, web text. But it needs massive storage. Finding the right sequence could be slow. And crucially, it's static. It can't adapt to what you're actually generating right now.
Yeah, a library of old text probably won't help if I'm writing, specific code or something brand new.
Exactly. Then there's PLD, prompt lookup decoding. It just looks for candidate sequences within the text you've already generated in that session.
Oh, so it can only repeat things.
Pretty much. Minimal cost, but it fundamentally can't predict new tokens or novel combinations. Useless if you need creativity or, say, translation.
Right, okay. And look ahead.
Look ahead tries to build a library of common short sequences, n-grams, but it actually makes the main LLM generate these m-grams during inference.
Wait, so it uses the slow model to build the library to speed up the slow model?
Yeah, the sources point out that's inefficient. You're adding extra work onto the main LLM just to build your guessing pool.
Okay, so the existing training-free options have some serious drawbacks. Huge storage, static data, can't generate new stuff, or they're inefficient. This really sets the stage for token recycling. What's its big idea?
This is where TR gets really interesting, and it's based on a core observation. You know how when an LLM predicts the next token, it actually calculates probabilities for many possible tokens?
Yeah, it gives like a ranked list and usually just picks the top one.
Exactly. It picks the top one, and all the other high probability candidates, the top K tokens, they just get discarded, thrown away. TR's insight is these discarded tokens, this trash, are actually really likely to be good candidates later in the sequence. their potential treasure. That's the foundational idea.
That is clever. Don't throw away the LLM's own close runners-up. Use them. So how does TR actually do the recycling, technically?
It's a three-stage process. Stage one is adjacency matrix initialization. Basically, for every single token in the LLM's vocabulary, they store the top K likely next tokens. And they put this into a compact structure, an adjacency matrix.
So like a giant lookup table saying the last token was A, the next one is likely B, C, or D?
Kind of, yeah. But specifically focused on adjacent probabilities. It captures the LLM's knowledge about very local patterns which token tends to follow which immediately.
Ah, okay. And you mentioned earlier this connects to how LLMs work, something about local patterns.
Exactly. The sources argue that the lower layers of these models are especially good at learning these immediate local connections, common word pairs, grammar rules for adjacent words. This matrix is designed to store exactly that kind of info.
Nice. So you capture the LLM's local knowledge efficiently. What else about this matrix stage?
Well, they use a hot start idea. If you've run TR before, you can reuse the matrix. It turns out these local patterns are pretty general, so starting with an existing matrix gives it a head start compared to building it from scratch. And the matrix format itself is key for fast lookups later.
Okay, so you build this matrix of local transition likelihoods. Stage 2.
Stage 2 is draft tree retrieval. So before the LLM generates its next token, TR looks at the last confirmed token. It then uses the adjacency matrix to quickly find likely next tokens, and then likely tokens after those, and so on, building out a small draft tree.
A tree of possible short sequences based on those local patterns.
Precisely. And the sources emphasize this tree has a static structure and is imbalanced.
Static and imbalanced. Why is that? Seems a bit rigid.
It's a performance optimization based on their experiments. Static means the shape of the tree, how wide or deep it can go, is fixed. This makes it really fast to process and verify using that tree attention mechanism we talked about. No time wasted figuring out the tree shape on the fly.
Okay, speed and imbalanced.
Imbalance means it prioritizes exploring paths in the tree that the matrix suggests are more likely. It puts more effort into the high probability guesses. It's a trade-off. Explore possibilities, but focus resources efficiently within that fixed structure. It avoids slow node-by-node checks.
Gotcha. So build an optimized tree of guesses based on the local patterns matrix. Then stage 3 must be checking those guesses.
Exactly. Stage 3, verification and update. This draft tree is passed to the main LLM. Using tree attention, the LLM evaluates all the paths in the tree in one go. It figures out the longest path starting from the last real token that matches what it would have generated. That whole correct path is accepted.
So you might accept several tokens at once if the tree had a good path.
Correct. And here's the crucial recycling part, the real innovation. During that verification, the main LLM still calculates those top K probabilities for every token it looked at in the tree, even the ones on the branches that got rejected. And TR takes all these newly calculated top K candidates from accepted and rejected tokens and uses them to update the adjacency matrix.
Wow. Okay, so the very act of checking the guesses generates new data to improve the next set of guesses. It's constantly learning from the current context.
Exactly. It makes the retrieval space dynamic, adapting to the content being generated. They use a parallel CUDA process for this update, and interestingly found that just merging the updates quickly was better for overall speed, tokens per second, than complex methods to perfectly avoid duplicates, even if MAT, the mean accepted tokens, dipped slightly.
Speed is king here. So going back to why this works so well, using those discarded tokens, it's more than just having a dynamic library, right? It's about the nature of those tokens.
Right. The analysis in the sources really points to this. LLMs capture local patterns well in early layers. The matrix stores this. A token might be discarded because it didn't fit the long-range context at that specific moment.
But it might still be a perfectly good fit locally, just one step later.
Precisely. The trash wasn't necessarily wrong, just not the absolute best fit globally then. But its local probability is still valuable information for the next step. And they proved this.
How?
In their ablation studies where they turned parts of the system off to see the effect, they showed that including candidates from the rejected tokens when updating the matrix significantly boosted the average number of tokens accepted, the MAT.
Ah, direct experimental proof that the trash really is treasure. That's compelling. So this whole clever system, recycling, discarded info, efficient matrix and tree, what kind of performance boost are we talking about?
The results are pretty striking. They report around a 2x speedup compared to standard generation consistently.
2 times faster. across the board.
Yeah, across different model sizes, they tested 7 billion, 13 billion, up to 34 billion parameter models, and across a real mix of tasks in SpecBench plus code generation, about 2x faster.
That's huge. What's the catch? Does it chew up memory or add a lot of computation?
That's the amazing part, almost no catch. The extra storage needed for the adjacency matrix is tiny, less than 2 megabytes.
2 megabytes. For models with billions of parameters, that's nothing.
Exactly. And the extra computation for retrieving from the matrix and updating it, negligible. Less than 5% of the total time. The speedup comes almost entirely from doing fewer passes through the main, slow LLM.
Wow. Less than 2 MB for a 2x speedup. How does that stack up against those other methods we discussed?
It blows the other training-free methods out of the water. The sources say it's over 30% faster speedup compared to things like Yukahead or REST. But maybe even more impressive,
Yeah.
it actually beats Medusa on average by about 25%. And Medusa is a well-known method that requires additional training.
Whoa. Okay, so a train-free method is beating a trained method by a good margin. That really speaks to the cleverness of the recycling idea. Does it work well on different kinds of tasks?
Seems to generalize really well. They tested it on conversations, translation, Q&A, math, RAG, and code. It showed strong performance everywhere. It's particularly good where there's repetition, like code.
Makes sense. Local patterns would be common there.
Right. And unlike static methods like REST, because its matrix updates dynamically, it's good at tasks that need genuinely new token sequences, like translation.
Broadly applicable, handles novelty. Okay, what about the absolute cutting edge, like Eagle?
They did compare it. It's competitive with Eagle 1, sometimes slightly better. Eagle 2 is faster overall, but Eagle 2 uses a more complex dynamic tree that adapts on the fly. TR gets about 91% of Eagle 2's speedup.
Okay, close.
We're using only, get this, 0.39% of the extra memory Eagle 2 needs for its draft components.
0.39%. Okay, that puts it in perspective. You're getting almost the same speed up for a tiny fraction of the resource cost. It really is like a free lunch speed up.
That's a good way to put it. No training, plug and play, tiny memory footprint, low overhead, dynamic adaptation, significant speed up. All from cleverly using discarded info.
It's clearly well designed. Let's maybe look a bit closer at those ablation studies you mentioned. They must give more clues about why the specific design choices work, like the tree structure.
They do. They played around with the tree structure, making it wider, more initial guesses, helps accept more tokens initially, higher mat, but make it too wide, and the verification gets slow, hurting overall speed.
Right, diminishing return.
And making it deeper, guessing further ahead, also helps mat a bit, but the benefit drops off fast.
Because the matrix is mostly about adjacent tokens, not predicting way down the line.
Exactly. The matrix captures local stuff brilliantly, but not deep context. So the static imbalance tree they settled on is basically an empirically found sweet spot to maximize tokens per second.
Makes sense. And the hot start. Using a previous matrix definitely helps.
Oh yeah, big time. The study showed hot start significantly beats starting the matrix from scratch. It proves those local patterns are pretty general, and carrying them off gives a real performance boost right from the beginning.
Good to know. What about the update strategies? He said the simple parallel update, one for speed.
Yep. They tried fancier ways to merge the new candidates into the matrix, maybe avoiding duplicates perfectly. Those sometimes got a tiny bit higher mat. But the simple fast parallel merge was best for tokens per second overall. The extra logic just wasn't worth the latency cost.
Simple is sometimes fastest. And the rejected tokens, the studies confirm their value.
Absolutely confirmed. Comparing updates using only accepted token candidates versus using candidates from all draft tokens, accepted and rejected, showed a clear, statistically significant jump in MET, but including the rejected ones. Direct proof for the trash into treasure core idea.
Solid evidence. One last thing from the studies. Temperature sampling. Does it only work for greedy, predictable text?
Nope, it holds up well. They tested with higher temperatures, adding randomness for more creative output. The speedup stayed robustly around 2x, even up to a temperature of 1 point out. Performance might dip slightly at very high randomness because the best tokens might fall outside the stored top K, but the acceleration is still significant.
So it works across different generation styles. Okay, we've really gone deep into the mechanics, the why, the cleverness, and the results of token recycling. Let's just step back. Why does this kind of acceleration matter to you, the person listening?
Well, on a basic level, it means faster AI tools. Your chatbot answers quicker. Your code assistant feels instant. It makes the interaction much smoother.
Less waiting, more doing.
Right. It also means more efficient use of the massive computing power these models need. That could eventually lead to lower costs for AL services. And maybe most excitedly, it opens the door for new real-time AI applications that just weren't feasible before because of the latency.
Yeah, it makes the AI feel much more present and responsive, less like you're sending a request off to a slow machine somewhere.
Exactly. Token recycling is a really neat technical step in that direction.
Okay, so wrapping up this deep dive, token recycling, it's this technically sharp, train-free, plug-and-play method. Its core genius is reusing those usually discarded top K candidate tokens.
The trash.
It stores them efficiently in a tiny adjacency matrix, uses a clever static tree for guessing, and verifies with tree attention. The result: about 2x speedup, less than 2 MB extra storage, beating many other methods, even some requiring training.
And it achieves this remarkable efficiency with that static tree. But interestingly, the sources themselves hint at a future direction.
Oh.
They mention the possibility of using dynamic tree structures, trees that could actually change their shape or depth based on a specific query, adapting the guessing strategy moment by moment.
So instead of a fixed guess shape, it could tailor its guesses on the fly depending on whether it needs to be careful or can make a big jump.
Potentially, yeah. Imagine how much more speed or efficiency that might unlock if the system could dynamically adjust its guessing strategy.
That really makes you think, what could truly adaptive guessing enable for LLMs in the future? It's a fascinating place to leave it.